Another interesting kind of polynomial which plays a central role actually. I mean, if you want to diagonalize a matrix, and it's also something important in its own. So it's called the minimal polynomial. So yesterday we talked about the characteristic polynomial of the matrix. So today we're going to talk about the minimal polynomial of the matrix element. So what's a minimal polynomial? So here's a definition. I'll do one example and then we'll do some properties of the minimal polynomial. So let A is a square matrix with entries from field F, and this field can be the field of real numbers or the field of complex number. A polynomial say let's denote that polynomial by M(a) of x. Okay, we're gonna call this polynomial a minimal polynomial. Minimal polynomial if it has the following properties. If number one, the leading entry, the leading coefficient in this polynomial should be 1. In other words, the coefficient of the highest degree term in this polynomial should be 1. Okay? So it's a monic polynomial. G of x is monic. That is the coefficient, okay, coefficient of highest degree term is 1 actually. Okay, so any polynomial in which the highest degree coefficient is 1 is a monic polynomial actually. By the way, characteristic polynomial is also a monic polynomial actually, because the first term of it is x power n. Okay, so it's a monic polynomial. Similarly, the second thing is, the important thing is that M(a) of x is a polynomial. Okay, is a polynomial of least degree, the smallest degree, such that it annihilates the matrix A, such that this polynomial M(a) of x annihilates A. That is that in this polynomial, if you substitute 0, A, you're going to get 0 actually. So it's a monic polynomial, and it's the polynomial of the least degree, okay, such that it annihilates the matrix A actually. Okay. Now we know that these both properties, in other words, characteristic polynomial is a monic polynomial, and characteristic polynomial is also a polynomial that annihilates the matrix A. But characteristic polynomial is not necessarily the polynomial that annihilates the matrix A, but it has the least degree. There can be other polynomials, okay, which are, smaller in degree than the characteristic polynomial, but they annihilate the matrix A actually. So any polynomial that annihilates the matrix A, okay, and has a least degree, you're going to call that characteristic polynomial actually. a minimal polynomial. And we will see, we'll prove a result actually, that the minimal polynomial has an interesting relationship with characteristic polynomial actually. Okay? Characteristic polynomial. What would be one example of it? For example, if you take the same matrix that we talked about yesterday, take this matrix 1, 1, 0, 1, then I know its characteristic polynomial is x minus 1 square actually. This is what the characteristic polynomial of this matrix is. But its monic polynomial, I know in the characteristic polynomial, if I substitute a, this is going to be 0. But if you take this polynomial, okay, then this polynomial is what do you call a minimal polynomial as well. Why? Because it has a leading coefficient, it's monic, and it has a smaller degree than the characteristic polynomial, such that in this matrix, in this polynomial, if you substitute the matrix A, you're going to get what do you call 0 actually. Okay, you're going to get 0. So it's the polynomial of the smallest degree, like degree 1, such that when you substitute A into it, it gives you 0. So for this matrix, PA of x is characteristic polynomial, while this is the minimal polynomial actually. Okay? Can we find the minimal polynomial in a systematic way? The answer is yes. There is as we have a systematic way to find the characteristic polynomial, that you need to compute the determinant of xi minus a. Question is, can we find the characteristic polynomial? Okay? A minimal polynomial in a systematic way? The answer is yes. And this is the lemma that allow you to basically deduce the characteristic polynomial, the minimal polynomial from the characteristic polynomial actually. Okay? So here's a lemma. Here's a lemma. So the lemma says, first of all, for a given matrix, square matrix Mn with entries f, the minimal polynomial is unique actually. You can't have more than one minimal polynomial for the matrix. Okay? So it is unique. Also, moreover, it divides, moreover, MA of x divides any other polynomial, that annihilates the matrix A. Okay? That annihilates the matrix A. So imagine you have a matrix A, square matrix A, and A of x is its minimal polynomial. And this minimal polynomial is unique. Moreover, if you take any other polynomial that annihilates the matrix A, like characteristic polynomial or any other polynomial, okay, then the minimal polynomial must divide such polynomial actually. So the minimal polynomial of the matrix A will always divide all other polynomials that annihilate the matrix A actually. In particular, it will divide the characteristic polynomial actually. So let's quickly do the proof of it. So here's a proof. Let us fix, let the degree of the monic polynomial is m actually. Let us fix the degree of the monic polynomial. Okay, and let P of x is any other polynomial, okay, of some degree, such that in this polynomial, if you substitute a, you get 0. In other words, it's an annihilating polynomial for the matrix A actually. Then I can do what? I can divide. By the way, the degree of the P must be greater than or equal to M actually. Okay? It must be greater than or equal to M. P of x is annihilating, in other words, P of A is 0, and the degree of the P of x must be greater than or equal to M. Why? Because the minimal polynomial is the polynomial of the least degree that annihilates the matrix A. So if this is another polynomial that annihilates the matrix A, then this polynomial must have degree greater than or equal to M actually. Okay. Now I can take this polynomial which has a lesser degree than P of x, and I divide, for example, the P of x by MA of x. I can, when I'm going to divide P of x by MA of x, I'm going to get a quotient polynomial and a remainder polynomial. Okay, I'm going to get the quotient polynomial and remainder polynomial. On dividing P of x by MA of x, we get what? The quotient polynomial, let's call it Q of x, and the remainder R of x, such that how they are related, okay, how they are related, that P of x is equal to quotient multiplied by the divisor, in other words MA of x plus R of x actually, okay, plus R of x. So in other words, this is the remainder theorem. The remainder theorem. When you're going to divide P of x by MA of x, you're going to get a quotient and a remainder such that P of x can be written as in the terms of Q of x and R of x in this manner actually. Okay? In other words, divisor multiplied by quotient plus remainder is going to return back the P of x. Where it is important that the degree of the polynomial R of x must be less than the degree of the divisor. Okay, it must be less than the degree of divisor. Why? Because if the degree of the remainder is greater than or equal to the degree of what do you call the divisor, you will still keep on dividing it actually. Okay, you will still keep on dividing it. So I hope before, for example, doing this or for making sense of it, try to do, for example, a long division example of dividing the polynomial actually. Okay, so when you're going to do this, this is going to make sense that you will keep on dividing the remainders by the divisor until the degree of the remainder becomes strictly smaller than the degree of MA of x actually. Okay? MA of x. Now, if in this matrix I substitute A of, in this matrix, if I in this polynomial, if I substitute, for example, A now. So let's substitute A in this equation. So you're going to get Q of A A of A plus R of A. Now I know that P of A is annihilating, this is going to be annihilating. I know that MA is also annihilating polynomial, so this will become 0 plus R of A. Okay, plus R of A. This means the R of A equal to 0. In other words, remainder is an annihilating polynomial for the matrix A actually. But that is going to be a contradiction to the definition of the minimal polynomial, because you have a polynomial that has a degree less than the minimal polynomial and that annihilates the, what do you call, matrix A actually. So this means this is not a minimal polynomial, because what is the definition of the minimal polynomial? It's a least degree polynomial, the polynomial of the smallest degree for which, you know, it annihilates the matrix A. Now you found, you know, a polynomial R of x that has a degree less than what do you call, the minimal polynomial, and it annihilates the matrix A. So this means this R of x must be 0. This R of x, in other words, this remainder should not be there, because if the remainder is there, you are getting a contradiction to the definition of the minimality. Okay? So if in this polynomial, in this, the remainder is there, okay, then you're going to reach to this contradiction actually, that the MA of x is minimal polynomial. So what is the best way to avoid this contradiction? That there is no remainder in this equation. So if there is no remainder in this equation, this means that the minimal polynomial divides completely the polynomial P of x actually. Okay? So this is a contradiction. This is going to be a contradiction unless you assume that R of x is 0. Okay, the remainder is 0. And if the remainder is 0, in other words, in this term you don't have this term, this means that the minimal polynomial divides the polynomial P of x actually. Okay, divides the polynomial P of x. P of x divides P of x. So what was P of x? P of x is any other polynomial that annihilates A, and we proved that the minimal polynomial must divide completely that polynomial actually. Okay, let's prove the uniqueness. So in order to prove the uniqueness, we need to assume two minimal polynomials. So let M star A of x be another